Welcome back, everybody. Mr. Johnson with you once again. This is Lecture 8, Section 3.6, Molar Concentration. And looks like I'm going to be a famous YouTuber because my channel just got its thousandth view, and I've got to assume that the advertising money is going to pour in soon. And I can retire from being a teacher and just sit back and talk into this microphone all day long. Wait, that's what I already do. Never mind. I guess I'll keep being your teacher for a while. As the name implies, molar concentration, we're going to be talking about the concentration today of solutions. Solutions are a homogeneous mixture where there's an even distribution of particles mixed in another substance. The solutions today that we're going to be talking about are going to be primarily aqueous solutions, where there's an ionic substance dissolved in water. The solute would be the ionic substance. The solvent, what it's dissolved into, would be water, giving us, again, an aqueous solution. This first sentence here suggests that many chemicals are dispensed in solution, and most chemical reactions occur in solution. And having done lots of chemistry in my life, I would agree. The majority of the reactions that I've done, or that we do for you, take place in solution. Goes on to say that concentration in general, not necessarily molar concentration, but concentration in general is any expression of the proportion of a chemical in a solution. And we're going to be talking about molar concentration today, which has its own specific definition. So I'm scrolling down a bit. And by the way, I'm on page 153 of my ebook. Pardon me for not having mentioned so already, or 145 of the textbook. So this is going to be about molarity, a type of concentration, the most common way we express concentration in chemistry. Molarity is the number of moles of the solute of what is being dissolved in a liter of solution. It did not say per liter of solvent. It said per liter of solution. So that volume, that liter, includes both the solute and the solvent. And together, they account for the total volume of the solution. Again, molarity is the number of moles of the chemical, but I'll say solute, moles of solute per liter of solution. So again, that's the volume of both the solute and solvent together. So as we look at this chart down below, we can see that molar concentration looks a bit like where from it we can write an equivalence statement. It is always per liter of solution that molarity is talking about. So it's always going to be in 1 liter of solution, how many moles of solute are there? Molarity is the number of moles of solute, X moles of solute per liter of solution. And as we know from any equivalence, 2 conversion factors can be written either with moles of solute on top and 1 liter, again, in the bottom, or with 1 liter in the numerator and X moles of solute in the denominator. And while there are 2 conversion factors that, again, can be written from this one equivalence, it's this left-hand one, moles of solute per liter of solution, that aligns with the definition for molarity, which, again, is moles per liter. We've got an example at the bottom. If we know the molarity of a solution, and it's 3 molar, then we know that in 1 liter of solution, there's 3 moles of that solute, in this case, 3 moles of hydrocyanic acid, or HCN, giving us either 3 moles of HCN per liter or 1 liter per 3 moles of HCN. So what we're going to be doing primarily for the rest of this lecture is using these conversion factors, either moles per liter or liters per mole, to convert from the known volume of a solution to how many moles it might have in it, or from known moles to what the volume might be, or we might bring mass in there as well, because we can do that, or maybe even particles. So here we go. We're going to flip our page, and I'd recommend that you take a moment, pause the video, and ask yourself if you know what 2 molar NaOH, 2 molar sodium hydroxide, means. One thing I may have failed to mention is that capital M stands for molarity, and it means moles per liter. So again, capital M is the abbreviation for molarity, which is moles per liter. So this means there's 2 moles of sodium hydroxide per 1 liter of solution. That, again, solvent is typically going to be water. So we've got 2 moles of sodium hydroxide in a total volume of 1 liter. So we're going to flip the page and solve practice problem 1 on page 155 of the ebook, which I've got highlighted here on the whiteboard. All right, so looks like we've got 0.72 liters of a 2.5 molar sodium hydroxide solution. And we want to figure out how many moles of sodium hydroxide there would be in that. Again, molar or molarity stands for moles of solute per liter of solution, so I'm going to write this out as 2.5 moles of NaOH per 1 liter of solution, just to remind us what this actually means. All right, so typically we start a problem by writing the given value. In this case, it's 0.72 liters in a DA box, and then using a conversion factor that gets rid of liters and moves us toward where we want to go. And we'll do that this time. So 0.72 liters NaOH. Back up a bit so you can see it. And then I know I want to use the conversion factor that has liters on the bottom and moles on the top so that liters cancels and I end up with moles. So 1 liter. Don't need to put solution there. Never a bad idea. And then 2.5 moles of NaOH on top. So liters will cancel. We'll multiply 0.72 by 2.5. Maybe take a moment to do that and see if you got the same answer as I did. So I got 1.8 moles of sodium hydroxide by multiplying these two numbers together. And notice I've got 2 sig figs in my answer because both of these numbers had just 2. All right, so now we're going to solve practice problem 3 together as well on the whiteboard, where we've got 3 moles of HCl. And the question is, how many liters or what volume would it take to have a 0.6 molar solution that has 3 moles in it? What would the volume of that be? Keep in mind, 0.6 molar means that there's 0.6 moles in a liter, but because we don't have 0.6 moles, it won't be a liter. So we're going to figure out what the volume would be. All right, so again, we got 3 moles of HCl, 0.6 molar solution. What would the volume be that would have that many moles in it? So I'm going to again write 0.6 capital M, molarity, in a way that's a little bit more meaningful. It's 0.60 moles of HCl per 1 liter of solution. Again, I'll begin by writing what I'm given, 3 moles. Because that's typically how I'll start. There'll be a point in the future when we'll realize that may not always be the best idea, but for now it is still. And like always, I need to figure out a way to cancel moles. I need moles in the denominator of this conversion factor. But molarity, by definition, is moles per liter. I can flip it, though, and write its reciprocal so that moles is in the bottom. So I write 1 liter of solution on top and 0.60 moles of HCl in the denominator so that moles cancels, and I'll be left with liters. So I'm going to divide 3 by 0.6, and that'll give me the volume of this solution that would have 3 moles of HCl in it. My calculator just gave me a 5, but because both of these numbers have 2 significant figures, my answer should have 2 as well, so I'm going to give it a trailing 0, which gives it that extra significant figure. So it's 5 liters of solution. That is my final answer, 5.0, excuse me. One of the most practical applications of what we just looked at using conversions and molarity is to prepare a standard solution from a solid. A standard solution is a solution of known concentration. For example, if we were to want to prepare a 1 molar sodium chloride solution, you could measure out 1 mole of sodium chloride, 58.5 grams. And because we know 1 molar is 1 mole per liter, that 58.5 grams would need to end up in a total volume of 1 liter. That's not saying that you would add a liter of water to the 58.5 grams, but rather you'd put the 58.5 grams in a flask and then bring the total volume up to 1 liter, so that the volume of a liter includes both the water and the solute. Little side note here, standard solutions are typically made in volumetric flasks, which are designed to prepare a solution of just a specific volume. So this is a 50 milliliter volumetric flask. It's designed to make a solution that's 50 milliliters. So let's say through some calculations that you found the solution you wanted to make, which you wanted to be 50 milliliters, needed 2.5 grams of sodium chloride. You'd weigh out 2.5 grams of sodium chloride on your scale, put it into the bottom of this, and then add water until you get to this, you can't see it very well here, this line, which is 50.0 milliliters. And that gives you a total volume of solution of 50 milliliters as opposed to a volume of water of 50 milliliters. And again, this is a volumetric flask. They come in all sorts of sizes so that you're able to prepare standard solutions of various volumes using whatever volumetric flask corresponds to that volume. So I'm going to flip my page to 156 of the ebook or 148 of the textbook, and we're going to solve practice problem 2 together on the whiteboard. Describe how to prepare 500 milliliters of a 1.5 molar calcium chloride solution from solid calcium chloride. One thing to keep in mind about this is that we are ultimately going to want to calculate the mass of calcium chloride that we'd need to weigh out on a scale to add, ideally, to that volumetric flask to then bring the total volume to a half a liter or 500 milliliters. Although we work mathematically in moles all the time, we don't have a mole scale. We can't weigh out a certain number of moles. So it's always grams that ultimately in lab we want to be dealing with solids because we, again, weigh things out in grams. All right, so we got 500 milliliters and we got 1.5 molar. I want to acknowledge once again that 1.5 molar is 1.5 moles. In this case, it's calcium chloride per 1 liter. And I won't say solution this time, 1.5 moles per liter. Well, if our goal is to get to grams, and we know that from moles we can get to grams, I think we're going to want to keep moles in our numerator and not have it cancel at first. So we're going to write 1.5 moles calcium chloride per 1 liter. If I were to put 500 milliliters right here, which is volume, the unit wouldn't cancel because liters and milliliters are not the same. So I'm going to convert liters to milliliters. There's 1,000 milliliters in a liter. I'm essentially dividing by 1,000. So this now would be the molarity in moles per milliliter. I converted liters to milliliters so that I can use this volume here of 500 mils. The other option is I could have just converted 500 milliliters to liters by, in my head, dividing by 1,000 and just used 0.5 liters. But we'll let the dimensional analysis work that out. So the next thing I'm going to do is put my volume here, 500.0 milliliters. And that canceled milliliters, leaving me with moles. So what I have here, represented through dimensional analysis, is the number of moles of calcium chloride that there would be in a 500 milliliter solution. Although I started by writing molarity and then I brought in the volume, I could have written my volume first and written my molarity second. I could have written 500 milliliters first, converted it to liters, and then multiplied by the molarity. The order they're written in doesn't matter. But I chose to start with molarity because I knew I wanted to get to grams, and if I knew I started with moles on top, that would ultimately get me to grams. So the next thing I need to do is convert moles of calcium chloride to grams. I'll use molar mass to do that. So I put 1 mole of calcium chloride on the bottom, and I put calcium chloride's molar mass on the top. I'm going to calculate it real quick. I'll be right back. So there's the molar mass of calcium chloride, 110.98 grams per mole. That made moles cancel, leaving me with the mass of calcium chloride that there would be in a 1.5 molar 500 milliliter solution, and I get 83.23 grams. But with only 2 significant figures, because of 1.5, my final answer is 83 grams of calcium chloride. And now we're going to do practice problem 3 on this same page, 156 of our ebook. What molar concentration of silver nitrate is produced by measuring out 1.8 grams and then adding water to make a total volume of 75 milliliters of solution? All right, let's think about how to start this. We want to find a molar concentration, a molarity. And we know molarity is moles of solute per liter of solution. So in the end, we need a value whose unit in the numerator is moles and whose unit in the denominator is liters. And if we get that, that will be molar concentration or molarity. Well, I'm given a mass of 1.8 grams and I'm given a volume of 75 milliliters. And we know we can convert mass to moles and we can convert milliliters to liters. So if I write 1.8 grams, and this is silver nitrate, in the numerator, of a dA box or a fraction or a conversion factor, whatever you want to call it, and I write 75 milliliters in the denominator of solution, I'm expressing a concentration. It's an amount of solute in an amount of solution. But instead of moles per liter, it's grams per milliliter. So what I just need to do now is convert the numerator from grams to moles and the denominator from milliliters to liters. I'm doing this all in one problem, in one dA problem. You could convert grams to moles in one problem, milliliters to liters in another problem, and then divide the moles by the liters. But I like to do it all at once. So I'm going to deal with my numerator first. I'm going to ignore my denominator and convert grams of silver nitrate to moles. Well, I found the molar mass already. I know that 1 mole of AgNO3 has a molar mass of 169.88 grams. And that converted grams to moles. So I have moles per milliliter. I'm close to molarity. I just need my denominator to go from milliliters to liters. So milliliters are here. They're in the denominator. For them to cancel over here, they've got to be in the numerator. Remember, they have to be opposite. So I put 1,000 milliliters up top, 1 liter on the bottom, and that converts my denominator from milliliters to liters. And what I have here, although I don't have the answer yet, is moles per liter. I just need to figure out how many moles per liter it is. And I get 0.14127 moles per liter. Looks like I need to round it to 2 sig figs. 0.14. Got a couple options at this point. I can just write capital M, because capital M means moles per liter, means molar concentration. AgNO3. Or I could have written, but I am inclined to write capital M, I could have written 0.14 moles per liter of AgNO3. It's more conventional, though, to use capital M, knowing that it means moles per liter. So there we are. There's our final answer. All right, so I've scrolled down a little bit, still on this same page, looking at the section titled Ions in Solution. I want to remind everybody that ionic compounds are formed from ions. So aluminum sulfate comes from aluminum ions associating with sulfate ions. 2 aluminum ions and 3 sulfate ions form the solid compound called aluminum sulfate. Well, if aluminum sulfate is soluble in and dissolved in water, and this is true of any ionic compound, the ions that associated together that formed that compound now disassociate or dissociate, meaning they are pulled apart by water and travel independently through the solution. And when we get to our solution unit, we'll look a little bit more about what that means. But aluminum sulfate, when dissolved in water, is not aluminum sulfate particles. It's aluminum particles moving freely from each other and moving freely from other sulfate particles. They're all moving around. Now, there are 2 aluminum ions for every 3 sulfate ions, but they're pulled apart and are functioning independent of each other, essentially, once they're dissolved in water. What we see down at the bottom, and we'll be writing a lot of these later, is what's called a dissociation equation that accounts for the fact that when a solid is dissolved in water, its ions dissociate from each other and are independent of one another, which is why we see the plus sign in there. So this reflects aluminum ions and sulfate ions dissociated from one another when aluminum sulfate has been dissolved in water. So we're going to flip the page and do a little bit more learning, and then we'll solve 2 or maybe 3 more practice problems, and that'll be the end of this lecture here in a little bit. All right, so we're on the next page, and I'm going to read this top sentence to you, which says, being able to relate the concentration of dissolved ions to the concentration of their parent compound is extremely important in chemistry. For example, if we know that we have a 3 molar aluminum sulfate solution, well, what would the concentration be maybe of the aluminum ions or the sulfate ions? The virtual lab that I hope to do with you next week or the week after is about water hardness. And we are going to be through, again, some virtual lab experiences, figuring out what the hardness of water is. Well, water hardness is a measure of the concentration of calcium ions. Calcium ions only dissolved in water. But calcium ions don't show up by themselves. They show up as a part of an ionic compound. Calcium chloride, calcium sulfate, calcium nitrate. So if we're curious to know what the concentration of calcium ions is, because we want to know what the hardness of the water is, we'd first need to know what the concentration is of the salt or the ionic compound that's contributing to the calcium ions, to the water hardness, to then figure out how hard the water is. And that'll make more sense when we hopefully do that lab in the next week or two. As you earlier heard me mention, a 1 molar aluminum sulfate solution does not mean there's 1 mole of aluminum sulfate particles dissolved in water. There's no such thing as aluminum sulfate particles, because once it's dissolved in water, as we know, the ions separate from or dissociate from each other. What this really means, because there's 2 aluminum ions for each aluminum sulfate, and there's 3 sulfate ions for each aluminum sulfate, that in a 1 molar aluminum sulfate solution, there'd be 3 molar aluminum ions, twice 1, and 3 molar sulfate ions, 3 times 1, because of the subscripts 2 and 3. So there's actually a higher concentration of ions, significantly higher concentration of ions, than one would think from just the molarity of the salt. We got 2 molar and 3 molar in a 1 molar solution. This sample problem gives us another opportunity to explore that concept. It's asking what concentration of ions are present in a 3 molar calcium chloride solution. Again, there's no such thing as calcium chloride particles. It dissociates into calcium ions and chloride ions. Well, there's 1 calcium ion per calcium chloride, and there's 2 chloride ions. So if we had a 3 molar calcium chloride solution, because there's 1 calcium ion per calcium chloride, the concentration would be 3 molar. But because there's 2 chloride ions, the concentration would be twice that. It would be 6 molar chloride and 3 molar calcium. Finally, on this page, down at the bottom, it says that the molar concentration of a chemical is indicated by putting square brackets around it. So if for a shortcut you don't want to say the molar concentration of sodium ions is, you instead can just put sodium ions in brackets, and that means the molar concentration of sodium ions. Again, brackets represent molar concentrations, and we'll be using that abbreviation quite a bit in the future. So I've flipped the page. I'm now on 158 of the ebook, and I plan to do practice problems 1, 2, and 4 with you on my whiteboard. And after we're done with those, that will be the end of our lecture today. So this first one, practice problem 1, what concentration of ions are present in a 1.5 molar calcium chloride solution, is just like we saw in the prior sample problem. So I've written out the dissociation equation, although I should put AQs, I'm realizing, next to these to suggest they're dissolved in water. And I'm going to put an S there to say that this is in its solid form, and this is the ions separated once they're dissolved in water. Well, calcium chloride is CaCl2, so for every calcium chloride formula unit that dissociates, we get 1 calcium ion and 2 chloride ions. It's a 1 to 1 to 2 ratio. And the molarities will adhere to this ratio, a 1 to 1 to 2. So if I've got 1.5 molar calcium chloride, I'm going to have 1.5 molar calcium ions and twice that, or 3.0 molar chloride. So there's a total, actually, of 4.5 moles of ions per liter of solution from a 1.5 molar solution of calcium chloride. All right, so we're trying to figure out what the molarity, or molar concentration, of sodium phosphate would be if we knew that there was 0.6 molar sodium ions in solution. That's what we did just backward. First thing we need to do is go from the name of sodium phosphate to its formula. Sodium is Na1+, phosphate is PO4 3-, little crisscross, and we get Na3PO4. Now you might be able to do this in your head, but I'm going to write it out explicitly and show again the dissociation equation for sodium phosphate once it's dissolved in water. So Na3PO4 solid dissociates into 3 sodium ions. And notice that I don't know that I mentioned this before, that when we write the ions dissociated from each other, we do include their charge, but when we write it as a regular formula, we don't. So that's 3 sodium ions and 1 phosphate ion, which is a 3- AQ. Getting tired, my handwriting is deteriorating. All right, so let's acknowledge that that's a 1 to 3 to 1 ratio. So the concentration of sodium ions will be 3 times that of phosphate and sodium phosphate. And if we know it's 0.60 molar sodium, then each of these values should be 3 times lesser. And that's going to be 0.20 molar phosphate, and what it's asking for, which is what concentration of sodium phosphate would deliver the 0.6 molar sodium, it's 0.20 molar also. And there's my final answer, 0.20 molar sodium phosphate. All right, last one. Little extra step on this one. What mass of potassium ions is in 0.75 liters of a 2.8 molar potassium solution? Know, though, that potassium ions cannot be in solution by themselves. They'd have to be in solution with some negative ions that came from the salt. But we'll assume they're there. All right, so we've got 2.8 molar potassium ions. Remember, molar is moles per liter, so I'm going to write 2.8 moles of K plus per 1 liter of solution. And my goal is to get to mass. I know through molar mass I can get moles to grams, so having moles in the numerator right now seems like a good start. I messed up. That should be 0.75 liters, not molar. All right. So I now want to get rid of my denominator because I want to just get the mass. And that's going to require me multiplying by 0.75 liters of solution. So liters of solution has canceled. And I'm left with just moles of potassium ions. But I don't want to know how many moles of potassium ions it is. I want to know the grams. So for moles to cancel, I put 1 mole of potassium on the bottom. And I put potassium's molar mass on the top, which is 39.10 grams. Be aware that the molar mass of ions will always be the same as their neutral corresponding atom, because the gain or loss of electrons, given that they're so non-massive, makes very little difference, negligible difference in the mass. So here's our setup. I'll go to my calculator, see what I get. Maybe try this on your own and see if you get the same answer as me. So when I did 2.8 times 0.75 times 39.1, I got 82.11 grams of potassium ions, rounded to 2 sig figs. Final answer, 82 grams of potassium. That concludes Lecture 8, and if you're wondering if in person I also make weird hand gestures when I'm talking, the answer is yes. Here I am doing something strange several years ago while teaching. Enjoy your afternoon, folks. It's been a pleasure being with you today. Take care. Make the world a better place.